All right, hi everyone. Welcome to this multi-scale modeling experimental presentation on transport and thermodynamics in concentrated electrolytes by Andrew Wang from the Monroe Research Group in the University of Oxford Department of Engineering Science. So within electrochemical systems, such as lithium-ion batteries, the electrolyte facilitates the transport of redox reactants to and from each electrode. And so it's understood that polarization of the electrolyte occurs during battery operation, and this can limit the overall performance. So to demonstrate this, I've shown a screen grab from the PyBAM, or the Python Battery Mathematical Modeling Tool, one of the very successful Faraday multi-scale modeling projects. And here we've used their code to very quickly and easily simulate a 4C sort of extreme fast charge for a conventional lithium-ion cell. And what you can see here is that there's actually a huge resulting concentration gradient that polarizes across the electrolyte phase. And so that's spanning a constant. So for a starting concentration of around 1 molar, that's spanning a concentration range from 0.4 all the way up to 1.8. And so associated with that concentration gradient is also a large potential drop across the solution. And so that's showing a potential drop of around 150 millivolts. And so you can see how polarization affects the efficiency of battery performance. Here, if our end goal was to charge up a battery to 4.1 volts, actually 0.15 of that is going to the electrolyte and not to the electrodes, where the charge is actually stored. All this is to say that we need to have a strong grasp on how concentration and potential gradients develop across space and time. And so to study the bulk electrolyte properties, we can actually replace the cathode and anode with symmetric lithium metal planar electrodes. Where here in this schematic, if we pass current in this direction, just to give a bit of intuition, we will be inducing a concentration gradient that is similar to this trace in red. And so when it comes to modeling electrolyte behavior, we want to understand current and voltage relations, where, if we apply a certain voltage or current, what is the response of that other property? And we also want to know locally varying microscopic states, or the composition of each species in solution across the entire domain. And so if we know this information, we can use it to inform things like fast charging protocols by navigating limitations such as ion depletion near the anode or these voltage cutoffs. And we can also optimize specific electrolyte formulations for specific applications. And we can also develop advanced mechanistic models where we can add these physics-based phenomena such as degradation reaction kinetics, where you can imagine if we know the composition of lithium ions and solvents and additives at the surface of each electrode, we can then write out how these compositions will affect the reaction rates of things like SEI growth. At the same time, we know that electrolyte properties are highly dependent on salt composition. And so recently, researchers have been reporting that they observe favorable functionalities for electrolytes going up to superconcentration. And so what you might lose out in terms of conductivity, having a lower conductivity, a higher viscosity, and high cost because salt is the most expensive component. We gain, you might observe improvements in a wider potential stability window, which might enable these higher voltage materials and improve rate capability, and also inherent safety because we have a lower fraction of that flammable solvent. And here we show an example taken from Tao et al., where a rate test with NMC 811 seems to perform better at higher rates with a nearly saturated binary electrolyte. And so it's really important that our model can fully capture the behavior of the transport and thermodynamic behavior of these superconcentrated electrolytes. And what we can show, with a fully characterized electrolyte using experimental methods, which we will go into in a moment, using experimental methods that are based on concentrated solution theory, we can then fully parameterize the electrolyte system. And so we can then use this fully parameterized electrolyte model and compare the model predictions to independent measurements for a polarization relaxation experiment. And so this was done with our collaborators at the Faraday Institute degradation team, particularly the Gray group over at Cambridge Chemistry. And so they have this technique based on in situ MRI, which can directly visualize the concentration gradients as they develop within a cell. And so we plugged in our independent measurements for diffusivity, transference number, and partial molar volumes, which parameterize the cation flux behavior across diffusion, migration, and convection. And from this animation, we can see that we get strong agreement between the model simulation and experiment for how our concentration of lithium ions are being distributed during this polarization relaxation experiment. But it's not enough to just show how these concentration gradients develop. Our experimental parameterization also allows us to separate out the voltage across the solution phase from the contributions of ohmic drop and a concentration over potential. And so you can see during that relaxation step, we can validate our parameters between the experiment and model. And what's quite interesting is that if you know everything in the bulk, you can actually accurately extract out the surface kinetic overpotentials, which will be useful for understanding lithium metal and other interfacial phenomena. So how do we actually measure these transport and thermodynamic properties? Well, we developed a suite of bespoke characterization methods that are designed to isolate each of these parameters. And so for partial molar volumes, we get these by measuring the solution densities. The transference number is measured with a custom machined Hitov cell, which is highly accurate and based on the solution densities. We use concentration cells, which we augment with the shifting reference method in order to maintain accuracy near saturation to then measure the thermodynamic factors, which are really important for extracting out liquid junction potentials. We then use restricted diffusion to get the Fickian diffusivities of the electrolyte solutions, and then EIS to get the ionic conductivities with a commercial probe. And so by applying this set of methods to LiPF6 in both EMC and in PC, we can accurately measure these transport and thermodynamic properties as a function of salt composition. And so to read more about the specific experimental details, I encourage you to check out our recent papers from our group with these citations here. And so these properties then parameterize a model which is based on concentrated solution theory. Now, it's especially important because we want to maintain applicability for superconcentrated electrolytes. And so in a binary lithium electrolyte, we have its main constituents, a cation, an anion, and a solvent. Now, for Nernst-Planck dilute solution theory, dilute solution theory only accounts for interactions between the cation and overall solvent and the anion and overall solvent, but not with each other. And so you can derive out an effective conductivity, diffusivity, and transference number. But with concentrated solution theory actually explicitly accounts for all of the pairwise interactions between all of the species. And so these key interactions, such as that between the cation and anion, cannot be ignored in the superconcentrated regime. And so there's also a thermodynamic factor, which I mentioned before is crucial for attaining those accurate voltage predictions from the model. We can also directly get insight into the solution structure for these concentrated systems. So with Raman spectroscopy, where we can probe the molecular vibrational interactions between bonds, we can see from the spectra as we get more and more concentrated, the shift in the blue peak shows that all of our solvent is being coordinated by salt. And that shift in the pink peak, we can see that ion pairing and higher order aggregates also occur in the superconcentrated regime. From pulse field gradient NMR, we can also see that ion association increases with concentration for the cyclic carbonate system. But for linear carbonate systems, they actually start off with incomplete dissociation in the first place. We can also see from densitometry that for superconcentrated electrolytes, salt occupies nearly 40% of the overall solution volume. And so this justifies the requirement to include a Faradaic convection term in our model. If you imagine 40% of the volume of our electrolyte is actually moving, you can imagine that this convection phenomena is significant. These experimental method developments, the further understanding of solution physicochemical phenomena, and our model simulation capabilities can then be applied to the Faraday standard electrolyte. And so this actually lets us further explore multi-component electrolyte models and expand our experiment and modeling capabilities, and let them span areas such as co-solvent additives and preferential solvation, where, for example, if we're adding additives such as VC or FEC, if we can predict their concentrations near the surfaces, we can also look into how SEI formation and degradation reaction rates are dictated by those surface concentrations. And then if we can also extract out these kinetic parameters based on the fact that we know everything that's going on in terms of the transport properties, we can then analyze things such as lithium metal plating morphology in relation to the electrolyte voltage response during plating and stripping. And so with that, I just wanted to thank you for watching this overview of our research. Wanted to acknowledge the Monroe Research Group, as well as our collaborators with the PASA Group and the Gray Group. And of course, a big thank you to the Multiscale Modeling Project and the Faraday Institution for supporting this work.